chemistry. In slide 3, we will start up with a functional group. In principle, generally speaking, functional groups is the most important aspect of organic chemistry. And what is functional group? Functional group, and from now on we will refer to it as FG. It's an atom or group of atoms which gives or determines the chemical behavior. Of a compound, of organic compound. So again, functional group is an atom or group of atoms determining the whole chemical behavior of organic compound. In other words, alkene, for example, in general, it reacts with bromine. It decolorizes the red color of the bromine and convert it into colorless compound. So if we have a compound contains only 2 carbons while containing the double bond, or a compound containing, for example, like 20 carbons or 30 carbons, both they will react the same way. They will react with bromine in presence of CCl4, and then the color of the bromine will decolorize, as we will see later on when we talk about the reactions. Was that clear so far? Is there any question? Please speak up with the mic because I cannot see you. I cannot see you typing. Is there any question so far about the functional group? Anyone speaks up? I'm sorry? Yeah, right, but I mean, is it everything is clear? The board is clear, the writing, everything is fine? Wonderful. Okay, so this is about the functional group. Now, in the slide number, I'm just going to mention the slide which I'm talking about. In the slide number 4, this is actually, as I said, since the functional group is the most important aspect of a compound, then let's start actually introducing the functional groups which we will introduce or which we'll study during this course. So let's start with functional groups containing multiple bonds or simply carbon, double bond or triple bond carbons. So as you have learned from maybe in the school, functional groups, some of the functional groups, first, compounds contain multiple bonds. Carbon-carbon multiple bonds. Carbon-carbon multiple bonds. So first one is alkene. And alkene, whenever we have carbon double bond carbon in a compound, then we have this functionality. And as you have studied also before in the school, if we have triple bond between 2 carbons, then we will call this alkyne. And in case we have this special system, what we have called it before, the benzene system. So this here we call it arene or aryl functional group. So we'll assume that there is no question unless you have a question, unless I hear someone talking in the mic, then I will stop talking and simply answer any question you may have. Do you follow me? So anyway, so these are 3 types of functional group of carbon containing multiple bonds. So carbon double bond carbon is alkene, carbon triple bond carbon is alkyne, and whenever we have this system, benzene derivatives, then we will call it arene or aryl groups. Now, if we have oxygen attached in a compound, then we will have group of functional groups, as you see in slide number 5. So whenever there is the carbon is attached to oxygen single bonded. Now we are not talking about oxygen carbon double bonded. So we have carbon oxygen. The first group, let's talk about the alcohol. If we have carbon attached to OH, then we have alcohol. If we have carbon attached to oxygen and then attached to carbon, then we will call this ether. As you can see here, the ether, we have the oxygen is attached to 2 carbons in general. So regardless of the hybridization of these 2 carbons, this will be called ether. Now, here, when we have carbon is attached to oxygen, it means actually in order to call it alcohol, it must be sp3 hybridized carbon. In other words, this carbon must be connected to 4 bonds. But, although it is not in the same slide, but it's just because we are talking about the carbon-oxygen functional groups, we have another group when we have the OH attached to this type of carbon, attached to aryl system. In this case, we don't call this alcohol, we call it phenol. Do you follow me? So, whatever the carbon is, as long as it is sp3 hybridized carbon, we will call it alcohol if it is attached to OH. But if the carbon here is attached to benzene system, then we will call it phenol. It's not alcohol anymore. If the carbon is attached to 2 carbons, regardless of what are these carbon, then we will call it ether. If the carbon is attached to any halogen in general, like the halogens here which we deal with, for example, F stands for fluoro, chloro, bromo, iodine, we will call it iodo. So if the carbon is attached to any of these halogens, then we will call it alkyl fluoride or alkyl chloride, alkyl bromide, alkyl iodide, depends on the atom which is attached to. Is there any questions so far until slide number 5? Any question? Speak up, please. Speak up. Any question? Yes? I'm sorry, I didn't hear your question. Just a second. Yes, go ahead now.
They cannot say that they cannot see clearly.
The what?
They cannot see clearly.
Who cannot see clearly?
We.
From the reflection, maybe, I don't know. But I was asking from the beginning of the lecture, do you see me? Do you see me clearly? Do you see the board? And I didn't get any response. Now, is it more clear? Is it clear, more clear now?
Yes, it's clear.
Are you sure?
Yeah.
Let me just see maybe the light. Is it more clear now? Huh? The most important thing is the board. Can you see the board well?
Yes, doctor, I can see.
All right, perfect. Okay, so let's just move. So this is what we were talking about, the functional groups when we have oxygen attached to a carbon. These are actually the functional groups. I'm not going to comment on everything unless there is something to talk about it. So please just go ahead and read them all, and then it will be a part of your study. Now, one of the most important functional groups in organic chemistry, which is when we have carbonyl containing compounds. If we have any carbon double bond O, whenever we have carbon double bond O, we call this group carbonyl. But as I said, this is a general functional group. It's not a specific functional group. So whenever we have carbonyl, that means this is the system which we are talking about, carbon, double bond carbon. And in this case, where there are several functional groups, each of which contains this carbonyl functional group, as you can see in slide number 6. So, the first functional group, when we have the carbonyl, C double O, this carbonyl, this carbon in the carbonyl attached to a hydrogen, and here any carbon. In this case, we will call this functionality aldehyde. While if the carbonyl is attached to two carbons, regardless of these two carbons, then we will call it ketone. And now these are the two, let's say, extremes of the carbonyls. Now, there are also, if we have carboxylic acid derivatives, so if we have the carbonyl is attached to OH, then we will call it carboxylic acid. If it is attached to amine, to a nitrogen, regardless of what are these groups are, we will call it amide. If it is attached to a halogen, this carbonyl, X here, regardless of what X here, we'll call it acid halide. You follow me? If it is attached to another oxygen and another carbonyl, such as R, C double O, O, C double O, R prime, for example, we call this acid anhydride. So these are generally the functional groups which are related to the carbonyl containing compounds. And the last one, which is the thioester, if we have a carbonyl attached to a sulfur, in this case we will call it like the thioester here, the thioester, it's like the ester, if you remember here, the ester OR, but when we have sulfur, then we'll just add thio to indicate the presence of sulfur in this organic compound. Any question? All right, as you can see in slide number 7, this is a survey of all functional groups, and by default, of course, you all must know these functional groups, and you should recognize the functional group present in any organic compounds as part of your general knowledge, which I am expecting from you. Do you follow? So this is all about the functional groups and the type of functional groups which we have. And then if there is no further question, we'll move to another phenomena of or in organic chemistry, what we call it isomers or isomerisms. So if there is any question, please ask now before moving to the isomers or isomerism in organic chemistry. Because of this phenomenon, actually, organic chemistry is a very expanded and very broad science. We have a huge number of organic compounds because of a phenomenon called isomers. And isomers simply, in principle, isomers, they are different compounds, of course, they should be different. As I said maybe from the beginning, this is abbreviation for compounds. So instead of writing the whole issue, for example, compounds, we will always abbreviate it by this way. So there are different compounds contain or have same molecular formula, but they have different structural formula. So in principle, isomers, as I said here, they are different compounds. They contain the same molecular formula, but they have different structural formulas. For example, the example here, which you have it, this is actually for the next slide, but since we are talking about, but anyway, actually before talking about isomers, we should explain the alkanes in principle. But anyway, we'll come to this later on. Let's talk about alkanes. Alkanes is a major organic functional group compounds in organic chemistry, and we call them saturated organic compounds. So alkane, in principle, they have a general formula of CnH2n plus 2. So these are the most saturated organic compounds ever. There is no organic compounds can have the ratio of number of hydrogens to the ratio of number of carbons exceeding this ratio. For example, we should recognize what's the general formula of alkane containing 5 carbons. If we have 5 carbons, that means the hydrogens, if it is alkane, must be 12, according to this formula. If we have a compound, alkane, contains 20 carbons, then definitely if it is 20, the hydrogens must be 42. So it's C20H42 if we are talking about alkane. Do you follow me? So saturated means the hydrogen to carbon ratio is the maximum. No other organic compound can have higher hydrogen to carbon ratio than اللي هو CnH2n plus 2. Do you follow me? So for example, if a student come up with an idea that he found a compound has the formula C15H, for example, 36, then we will definitely say this compound cannot exist. This is not an organic compound. It will never be an organic compound because the maximum molecular formula of a compound contains, or alkane contains 15 carbons, will be C15H32. Do you follow me? regarding the aliphatic and regarding the saturated alkanes? Any question about it?
No, doctor.
All right, thank you. All right, so let's get back to the isomerism and the first type of isomerism, what we will call it now constitutional isomers. But in principle, as I said, isomerism as a phenomena is responsible for the huge number of organic compounds which we habit, which present in life. Now, in principle, we can simply express the structure of organic compound, or the structure of organic compound, the carbons in organic compounds can be connected in two ways of connecting carbons in organic compounds. Let's say two ways of carbon atoms connection. We have what we call it long chain, and we have what we call it branched chain. In the long chain, the number of carbon to carbon atoms, bonds, must be not exceed than 2. In this case, for example, let's take hexane. Hexane, as you will see, it is simply CH3, CH2, 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 CH3. As you can see here, this carbon is attached to one carbon. This carbon is attached to two carbons. This is to 2, this is 2, this is 2, and this is 1. So in other words, in the long chain, carbon attached to either one or carbon attached to two carbons. But whenever we have carbon attached to carbon or more, attached to 3 or more, then we have a branched chain. For example, another example of this can be CH3, CH3, CH2, CH2, CH3. So as you can see here, we have 6 carbons attached in a long chain like this. We have here 6 carbons attached in a branched chain. This is called branched. Why we call it branched? Because as you can see here, this carbon is connected to 3 other carbons. So whenever we have at least 1 carbon or more, this carbon is connected to more than 2 carbons, then definitely we will categorize this as a branched chain alkane. So we have straight chain or long chain, straight, long, or straight, the same. Or we have branched chain in organic chemistry. Is that clear for slide number 10? Clear? All right, I will assume that it's clear. Now, let's go back to what we said is the isomerism and isomers. And in the isomerisms or isomers, as I said, these compounds, they have the same molecular formula, but they differ in their structural formulas. So again, let me write it in here. Isomers, they have same molecular formula. So let's assume, let's agree on something instead of too much writing on the board. Molecular formula, we will always appreciate it as MF. So the MF stands for molecular formula. Now, structural formula, we will abbreviate it by SF. So SF stands for structural formula. And why we care about these two formulas? Simply because these are the identity, they will determine the identity of any organic compound for us as chemists, as organic chemists, in order to recognize and to understand the behavior of organic compound, we need first to know what's the identity of the organic compounds. What's determining the identity of the organic compounds are these two things, molecular formula and the structural formula. Just to remind you, if some of you forgot what you have learned in General Chemistry 2101, what's the molecular formula? The molecular formula, it's a formula that gives us information about the number and the type of atoms present in a compound. For example, molecular formula can be C5H10O, like this. So what we will know from this here, that we have 5 carbons, we have 10 hydrogens, we have 1 oxygen. So molecular formula gives us information about the type and the identity of the atoms and the number of each atom present in a compound. But here, knowing this knowledge only is not enough, because it will only give us just this formula, but it will never give us what's exactly the structure of the compound. In order to combine both, we need to know what's the structure of the compounds, how these carbons are connected to the hydrogens and oxygen. So there are several ways of simply connecting these carbons to each other. And every way will give us a new compound. That's why actually where we have the isomers now. So the isomers here, they are, as I said, they are compounds having same molecular formula. So they are always same molecular formula, but different structural formulas. So that's always the isomers. So any 2 compounds or more, they have this condition, then we will call them isomers. The first type actually, which you have it in slide number 11, is the constitutional isomer. So the first type of isomers, what we call it constitutional isomers. And what are the constitutional isomers? The difference in the structural formula, so that they have different connectivities of atoms. Do you follow me? For example, let's say we have a formula of C4H10, alkane of this formula, C4H10. There are several ways of connecting the carbons to each other in this example. For example, we may have the long chain where we have the carbons are connected in a long or straight chain like this, which we call it N-butane, as you will see in the coming slides. Or we may have the possibility that the carbon skeleton are like this way, CH3, CH, CH3, then CH3. This is called actually as a common name, we will call it isobutane. Of course, as IUPAC will call it differently, it will be called 2-methylpropane, as we'll come to this later. But here we will have 2 compounds or 2 different structural formulas for the C4H10. Now, why we categorize it under this categorization, the constitutional? Because as you can see, the connectivity of carbon skeleton here is different. You see, here we have carbon connected to carbon, carbon, carbon. But here we have carbon connected to 3 carbons in this case. That's why this type of isomers, we will call it constitutional isomers. Is there any question? Any question? Go ahead, please.
No,
Everything's fine? All right, perfect. So this is about the constitutional isomers, and as you can see, there are several examples. You have it in your slides. You can just check it out and see if there is. Now, just look at this table, actually, what you have it in slide number 11. As you can see, as the number of carbon increased, constitutional isomers, or the isomers which we may draw for the same molecular formula, it will be higher. So you can imagine just a formula of C30, when we have a compound with 30 carbons, how many isomers we may draw for this compound. It's like 4 billion and something, or number of compounds, which simply explains to us that this phenomena, the isomerism, is responsible actually for the huge number of organic compounds which are present in nature. Now, as a practice, actually, please draw all constitutional isomers of the formula C5H10. So please draw all isomers. Let me just write it. Draw all isomers of this formula. You must find for the C5, as you can see in the table. Sorry, write it for the C6, not C5. Make it for C6 in order to have good number, actually. C6H12 then. In this case, you should expect to have 5 compounds. You must find 5 isomers of this compound. Draw them all. Find them. How we could find or draw all isomers of the compound. Yes, please. Go ahead. حرك الكاميرا على اليمين يعني this side ولا oh sorry it's okay or maybe I move the board better this way. Is that fine now?
Yes.
All right. Okay. So please do this just to understand the isomerism in a good way. Now, there are several ways of representing organic structure. There is, of course, the detailed structural formula, and there are condensed structural formula. There are several ways, as you can see in your textbook. In the condensed structural formula, we have, of course, the detailed structural formula to write everything. For example, such as if we want to represent the structure of your butane, if we want to draw everything about the structure of your butane, it will be like this. So C hydrogen, 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 attached to C hydrogen, hydrogen, C hydrogen, hydrogen, and so on and so forth. To draw all of this structure, first of all, it's not practical. Secondly, as you can see, it takes a huge space actually for drawing such a structure, such a complete drawing of the structure. Do you follow me? This is only for a compound contains 4 carbon. Imagine if we want to draw a compound contains 20 carbons, how much space we will need and how much time we will need. Instead of drawing like this, we may the condensed structural formula, we don't show the bonds here. We just draw it like a collection of groups. For example, here we have CH3 attached to CH2, then CH2, then CH3. We may draw it also by this way, CH3, then CH2, and this is in the middle, attached to 2, then CH3. This is called condensed structural formula. Instead of drawing this or that, the best drawing of the structure, or the most practical drawing of the structural formula for compound, what we call it the bond line formula. And in the bond line formula, we just use lines to present any compound. For example, here this compound is actually C5H10. How we do so? What's the bond line formula exactly? In the bond line formula, hydrogens are not shown. So we don't show hydrogens. Why we don't show hydrogens? We don't need to show hydrogens. It is by default. We will know the number of hydrogens needed to be connected to each carbon. So this is one. Now, secondly, each bond represented by a line, just line like this. And any intersection or end line is carbon. In other words, this is here, this is a carbon because this is the end line. This is again another carbon because it's intersection of two lines. This is again another carbon, it's intersection. Again another carbon, again another carbon. So what we can conclude from this bond line formula is that we do have 5 carbons. So then, in order to know the molecular formula, how many hydrogens we have? If this is carbon attached to one carbon, then by default, this is a CH3. It needs to be attached to 3 hydrogens. If this carbon is connected to 2 carbons, then it's definitely CH2 because in order to have the tetravalent or the tetravalency. The same thing applies to this hydrogen. Yes, please. This way? Oops, no. Because I don't see actually what I'm drawing. Let me just keep looking at the camera. Oh, okay. You're right. Yeah, I know. Okay, perfect. So anyway, I'll just very quickly try to ignore the slides just because I want to see what I should teach anyway. So as you can see in the bond line formula, here any end line is a carbon and any intersection of any 2 carbons. For example, what's the molecular formula of this compound, guys? Can you see it? What's the molecular formula of this compound? Anyone knows?
C4H8.
C4H what? H10. Right? It is C4H10. Or it's not actually, not C4. It is C5, not C4. Right? So this is wrong. Now here, how many carbons here? We have this intersection, it's 1 carbon, isn't it? We have 1, 2, 3, 4, and this one is 5. So it is C5. Since all bonds here are single bonds, we should conclude that this is alkane, which means it is saturated, which means it must fulfill the CnH2n plus 2, which means C5H12. Why? To prove it, this carbon is attached to only 1 carbon. That means this must be a CH3, isn't it? The same applies to this one. The same applies to this. Same applies to that. And the one in between, in the middle here, it's a carbon attached to 4 carbons. That means there's no hydrogens in it. Is that clear? Do you follow me? Yes, Jihad, it is C5H12, exactly. Any other question about it? All right. So I'll just move this. Let me just, again, just give you another example for the bond line formula. Suppose we have this here. What's the molecular formula of this compound again? Please try to answer it even by chat, but just drawing the structure. Salim, is this C9 or C10 or C9? Okay, let's do it together. Now this is C9 actually. It's just see this, the number of carbons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. Here, this intersection, we have oxygen. So the rule here, just to add or modify what we have said before, any intersection is carbon unless another atom present in there. For example, such as oxygen, nitrogen, sulfur, anything in here. Do you follow me? If that's the case, that means this is not carbon, it's just that atom which represents the intersection. So we have C9, and of course the number of hydrogens you can simply make it by slowly by this way. This is a CH3, this is a CH3, this is a CH for sure because it's this carbon connected to 3. This is again another CH, and this is a CH3. Again, this is a CH3, CH3, and CH3. So how many CH3s? 1, 2, 3, 4, 5, 6. 6 times 3, that means we have 18, and then 20. So H, 20, and then oxygen. So this is the correct molecular formula for, yes, C9H20O. Exactly, perfect. That's exactly the molecular formula of this bond line representation. Please take this into consideration that you must, from now on, you must be able to convert any bond line or any structure to the bond line formula, and to recognize the molecular formula of any bond line formula very quickly. Yani you shouldn't take, well, we just make it slowly now and in a relaxed way, but in the real time you should recognize the molecular formula very quickly in order to proceed further for the next step or for the next understanding of the topic. All right, let me just see here. Now, for the name of the straight chain, you have in table here in the slide number 13, the names of the straight chains of alkanes, starting from carbon number 1 to carbon number 30. You should, or you must, know and memorize these names. These are the basics of all names in organic chemistry, where actually some of the students may think organic chemistry rely on memorization much, and which is really not true. These names here are just the basics. You will use them exclusively for any other organic compounds, but without knowing these bases, you will never be able to apply the rules of the IUPAC nomenclature, as we will discuss and explain in the coming slides. Do you follow me? So you must recognize all the time now that if any compound, organic compound, contains only 1 carbon, that means it must be methane. If it is 2, then the basics of this compound must be ethane. 3 propane, 4 butane, and so on and so forth. So these are the basics. So please, next lecture, actually I assume that these the basic names of the same chains, you have already studied them in the school, but in from next lecture you supposed actually to memorize them fully if for any reason you have forgot them. Any question about it? All right. So beside now, you can see here from this table. Now there are certain alkyl groups, what we call it. So alkane has the general formula of CnH2n plus 2. Now in organic chemistry we exclusively use the term of alkyl group. And the alkyl is just simply CnH2n plus 1. Means the alkyl group, the relationship between the alkane and its corresponding alkyl group is that alkyl is missing of a hydrogen from by the alkane, or alkane here simply is alkyl group plus hydrogen, or the alkyl is alkane minus hydrogen. It's either the way you would like to. For example, from this table, the chapter in the table, slide number 13, the CH4, we call it methane, right? If we have a group like CH3 attached to something, then here you see CH3 is coming from the CH4. It's the alkane. This is the alkane. Now this is the alkyl. The group here, simply the name of this group will be from the alkane, but instead of the "ane" here, we will replace it by "-ile." In this case, this will be or should be methyl group. Do you follow me? Another example. If we have CH3, CH3. From the table here, you have it, or its name, it must be ethane. So ethane is the name of the alkane, right? You just see the view of the camera, right? The ethane is the alkane. If we have it CH3, CH2 attached to something, in this case, instead of ethane, we will replace it, or we will call it ethyl. So the alkyl group, always we replace the "ane" by "-ile" becomes. So دايما the alkyl group coming from certain alkane. So the name of the alkyl group, we just replace the "ane" with the "-ile", and the beginning will be the same. فبالتالي if it is propane, it will be propyl, ethane, ethyl, methane, methyl, and so on and so forth. But sometimes we may have also more advanced branching and more advanced naming, and therefore we may use it actually this way. For example, let's see the propane. So we have CH3, CH2, CH3. So this is the propane. Now as you can see here, there are two different ways of the hydrogen to be connected to another chain or whatever in the future, as we will see. For example, the loss of the hydrogen can be at the end of the chain, in this case from here, or it can be CH3, CH3, then it could be from here. Can you see these two different alkyl groups? So both are alkyl group from the alkane, because they are missing one hydrogen only. In this case here, in order to distinguish this from that, we will call this propyl or N-propyl, just propyl. Here's just we replace the N with the I. But in here, in order to distinguish it from the propyl, we will call it isopropyl. Do you follow me? Any question? Is there any question? Perfect. So this is actually how to name the alkyl groups. So this is for the propane, the 3 carbons. Let's go forward to the 4 carbons and see what alkyl groups can be derived from the 4 carbons. So let's simply instead of writing here, just replace it to CH2, then CH3. Now, this is here, it's exactly like the propane. We have 2 possibilities that missing of the hydrogens to be, either from the end of the chain or from this carbon. بمعنى, we may have it like CH3, CH2, then CH attached from this side to another chain, CH3, or we may have it from the end of the chain, CH2, 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 then CH2, then from this side. So this here, always from the end of the chain, we'll just replace the N with the I. بمعنى, this was butane, so this here will be butyl. That's it. Here, we similar to the isobutane, propyl, but we're not going to call it iso, we'll call it secondary. Oops. Secondary butyl. Or we call it abbreviated by secondary butyl. Or we may call it S-butyl. It's actually, secondary is the best all the time, just to call it like that. Either we call it secondary or secondary butyl. Do you follow me? This is the way how it is actually. This is just to distinguish if the loss of the hydrogen from the end of the chain or the loss of the hydrogen from the carbon which is in between. You follow me? There is another option even. There is another possibility for the alkyl groups derived from the butane. So all are derived from the butane. In this case, if we have...
دكتور
Yes, please.
على أي أساس أسمي secondary ولا iso؟
That's a good question actually. It's no basis here. This just like we agreed to do this because this is like common names and we agreed to make it like this way. This is how we distinguish this from that. It's like just giving names. The names here, giving the names, is like agreement of the scientific community rather than to make any like logical explanation or whatsoever. Do you follow me? We should accept the name as such in this case. Do you follow me? There is no logical explanation for this rather than that the scientific community of chemists who are dealing with the nomenclature, they agreed to do so. You follow me?
Yes.
All right. Now the other option actually where we have, which can be where we have alkyl groups derived from the butane, that we may have another 4 carbons that they are connected in a branched way, this way. Now this compound, commonly it has the name of isobutane. Do you see? Now why we call this isobutane? Again, it's just common name, isobutane. In the isobutane, which is 4 carbons, again we have 2 possibilities for the hydrogen to be missing from this alkane, and thus we will have alkyl. Either the hydrogen of this carbon to be missed or this carbon. If it is from the chain, CH, CH3. This is from the end of the chain, CH2, whatever. This here we call it isobutyl. Do you see it? If it is from the carbon in the middle, we will have it like CH3, C, whatever, CH3, and then CH3. We will call this tertiary butyl, or we call it tertiary butyl, or we call it T-butyl, just to distinguish it from each other. I think it should be, it's a little bit. Do you see it? Can you see what I'm saying?
Yes.
Perfect. So as you can see here, we have for the carbon, 4 carbons, we have several alkyl groups. It can be secondary butyl, can be butyl, can be isobutyl, can be tertiary butyl. So these are actually the derivatives of the alkyl groups coming or derived from the butane, or in other words, an alkane connected to 4 carbons. So we have 4 alkyl groups in this case. Now you can see it now as the number of carbons increases, definitely the possibility for alkyl groups are increasing further. For example, methane only 1 alkyl group, which is the methyl. Ethane only 1 alkyl group, which is the ethyl. Propane, there are 2, isopropyl or isopropyl. Butane, we have 4, either butyl or secondary butyl or isobutyl or tertiary butyl. Now then definitely when it comes to more carbon, then we will have more and more alkyl groups. That's actually for the alkyl groups, and I think I will stop now because I have noticed from your emails that there are plenty of questions about something related to chapter 2, which is specifically the resonance structures and how to draw the resonance structures. Due to the importance of the resonance structures in organic chemistry, I would like to dedicate some time to answer some questions, and if there is any further question, please let me know regarding the resonance structures. Next lecture will continue from after the alkyl groups, but now I'm just going to solve maybe the problems which I have sent to you by the WhatsApp group, which was, I think, question number, chapter 2, question number 25 and 26, 27, I don't know. Anyway, I'll just look at them. Now, chapter 2, I think question number 25 was like this. It shows the curved arrow of the movement of the electrons of this compound when this reacts with H+, or when this behaves as a base. Of course, in the organic chemistry, this is the structure of this compound, or this is the Lewis structure, but it is not shown fully the lone pairs. And you must know from your knowledge that the oxygen here, it always contains, if it is bonded to 2 atoms, then definitely it needs another 2 lone pairs in order to reach the octet. So therefore, we should expect that we have 2 lone pairs at the oxygen. In this case, according to what we have defined, the Lewis acid and base, this is, of course, this is Lewis base. Because the Lewis base is always any species or any substance which can donate a lone pair. So there we have lone pairs here to be donated. That means here, this hydrogen, of course, it can accept the lone pairs. So this is for sure, it's the Lewis acid then. For sure here, the reaction here will be, this lone pair will be given to the H+, and thus we will have a new bond formed between the oxygen and the hydrogen. In this covalent bond, the oxygen contributed by 2 electrons, while the hydrogen did not contribute by anything, which means the hydrogen will simply lose the positive charge, while the oxygen will carry the positive charge. Because as I said, this covalent bond has been formed by the contribution of the oxygen only. It's the oxygen electrons which made this bond. Therefore, the oxygen in this case must, or the formal charge of the oxygen must be always plus. This is, of course, a detailed explanation of the whole issue. But from now on, you should recognize, as organic chemistry student, you should recognize all the time